Question 7. Figure 2 shows sketch of part of the curve C with equation y is equal to x cubed minus 10x squared plus 27x minus 23. And the point P, 5 minus 13, lies on curve C, and the line L is tangent to the curve at this point. Part A, use differentiation to find the equation of L, giving your answer in the form y equals mx plus c, where m and c are integers to be found. Well, if we have the tangent to a curve, we can find the gradient at that point if we have the gradient function of the curve. So, starting with our curve C, which is y equals x cubed minus 10x squared plus 27x minus 23, we want to differentiate this to find our gradient function. So multiply by the power, reduce the power by 1, x cubed differentiates to 3x squared, minus 10 times 2 minus 20x, because 2 take away 1, 27x differentiates to 27, and minus 23 being a constant differentiates to 0. So we have our gradient function. At the point P, x is equal to 5. And so substituting 5 into our gradient function, so substituting x is 5 gives us 3 lots of 5 squared minus 20 times 5 plus 27, which evaluates to 2. So our gradient at this point is 2. Now we have the point P, so we have a coordinate 5 minus 13. We know the gradient is 2, so we can put this into our equation of a line formula, which is y minus y1, which is minus 13, is equal to the gradient times x minus x1, so 5. Expanding the brackets here and dealing with our double negative, we've got y plus 13 is equal to 2x minus 10. Subtracting 13 from both sides gives us y is equal to 2x minus 23, which is the form mx plus c. Part B, hence verify L meets C again on the y-axis. Now if C and L both meet on the y-axis, then when x is equal to 0, they both pass through the same point. So let x equal 0. Let's look at our line equation that we've just found. So y is equal to 2 times 0 minus 23. So y will be equal to minus 23. On our curve, substituting in 0 again, we'll have 0, take away 0, plus 0, minus 23. Therefore, both of these lines will cross at the point 0, minus 23. Part C, the finite region R, shown shaded in figure 2, is bounded by the curve C and the line L. Use algebraic integration to find the exact area of R. So the first thing I'll do is, looking at this diagram, we consider this point P here and draw a vertical line. And between the values of 0 and 5, the values of our curve C are always greater than the values of our line. And so we can find the area bound by these two by integrating the equation of the curve, subtract the equation of the line. So this integral then becomes between 0 and 5, x cubed minus 10x squared plus 27x minus 23, minus 2x, and then minus 23 plus 23 dx. This simplifies to x cubed minus 10x squared. We've got 27x minus 2x, so plus 25x, and our minus 23 and plus 23 will cancel. This is a nice integral to do. Increase the power by 1 and divide by the new power. So this x cubed becomes x to the power 4 over 4. Minus 10x squared becomes minus 10x cubed over 3. And plus 25x integrates to 25 over 2 x squared. And this is a definite integral between our limits of 5 and 0. When we have a definite integral, we substitute in our upper limit and then our lower limit. So this becomes 5 to the power 4 over 4 minus 10/3 of 5 cubed plus 25 over 2 5 squared. And now substituting 0 into each of these terms, it will all be 0. So subtract 0. These values here then, we could jump straight to a calculator to type this in one go, or you could work out each value individually. It becomes 625 over 4 minus 1250 over 3 plus 625 over 2. And again, on a calculator, we get a value of 625 over 12, which is our area R.